Alright, so this is going to be the video that I promised you earlier today. We didn't finish all of the problems in class, so I wanted to go through and do some of these problems for you. They're going to involve things we're going to see in the future. Some of them have involved things you're going to see in your homework. So for this first one, when I put this 19 here, I do mean that this is actually not problem number 19, but this is the 19th derivative on that opening flap when you open your textbook. So remember I showed you their reference page with derivatives and integrals. It's the 19th one out of the 36 that are on that page. So it says something super crazy. It says that when we take the derivative of our inverse sine or arc sine, we're going to get something that has no trig functions involved in it. We get something with a square root. It's an algebra equation, and that's wild. But I'm going to show you how we got that, and it's going to lead to how we got some of those other inverse trig function equations. So I want you to remember, I've put over here a triangle, and I've made one that is on the unit circle. That's why the hypotenuse is 1, the opposite side is y, and the adjacent is x. We only see that on the unit circle. And just as a reminder, your sine of theta is opposite over hypotenuse, which in this case is y over 1, or just y. And the inverse sine, the purpose of it is if you know the ratio, but you don't know the angle, it helps you to find the angle. Now I'm going to do some rearranging of variables. I'm not going to use exactly what came off of the unit circle. Instead, what I'm going to look at is, I want a y equals equation. So let's play with the equation y equals the inverse sine of x. So our arc sine function set up as a just traditional method, y equals blah blah blah. And I also should point out, you might notice here I wrote it as arc sine, here I wrote it as inverse sine. It is true that these are actually the same thing. You're more likely to see arc sine in a textbook and more likely to see inverse sine on a calculator. Although you will see them go back and forth, they are equal to the same thing. So anyway, I just have it written in my generic form. And I want to focus on what is the derivative of this trig function, inverse trig function that I've not played with before. So to do that, I'm going to pretend that I don't know this yet. In fact, I don't. I need to prove it to you. So I am going to use the inverse of my inverse. When I say that, remember, if I'm going to rearrange the equation to get rid of my inverse sine, and you can see I did it over here, I can say that my sine of my y is going to be the same thing as my x. It's how I can switch the variables back and forth. These are actually going to be the same line if I graph them, so long as I keep the x's and the y's the way you see it on the screen. Now what I like about this is I can take the derivative of this. That is nothing new. I can take the derivative and do it of both sides based on the rules that we have learned so far. So my derivative of the left-hand side is going to be 1. The derivative of the right-hand side, we learned today we are going to have to use implicit differentiation because our variables do not agree here. So I will get, now remember, take the derivative like you normally would. We're going to start by taking the cosine of y. And then when they don't agree, you have to tack on this dy dx term at the end. So my derivative is going to be, if I move this cosine of y to the other side, right there, dy dx is equal to 1 over the cosine of y. Now, we are going to, I've said before many times in class, trig identities play a part in what we do this year. They're going to pop up just randomly. This is why I wanted to practice with them a little bit at the beginning of the year, because we're going to see them off and on throughout this year and in the future with whatever math classes you choose to take. And one of the most famous is going to be this idea that sine of theta plus cosine of theta is equal to 1. I can use that to solve for cosine of theta. And something that will always be true, because a trig identity is true no matter what angle you plug into it. So if I take sine of theta plus cosine squared of theta equals 1, and I subtract the sine squared over, I get cosine squared theta equals 1 minus sine squared theta. And you might notice that this is starting to look like what I want. In that, there is a square root now, and under the square root, a 1 minus something squared. I can take that and I can substitute in. Of course, I'm going to change my variables to y's, but I can substitute in that this is the same thing as 1 over the square root of 1 minus sine squared theta. Oh, again, not theta, y. Now, there again, some more substitution on this problem. If I come back up here, I have a definition for sine of y. I can substitute that into my problem, and voila. I get out that the derivative of my inverse sine of x is equal to 1 over the square root of 1 minus x squared. And remember, this is the derivative of the inverse sine of x. I had only changed it to this form with the positive or the regular sign because I didn't otherwise know how to find the derivative of the inverse sine function. But by switching the location of my x and y and changing it to a sine function, I can use rules that I've already learned to establish this. Now, I'm not expecting that you're going to be any sort of pro at this right now, but I do want you to practice with it because this is going to be the sort of thing we're going to have to play with. You definitely will see some of these problems on the AP test, meaning you will have to take the derivative of the inverse of sine or another trig function, but you probably won't have to prove it like I just did. Might come up in a homework that I throw at you. Anyway, I can do more of those sometime, but right now I'm going to move on to a problem that we skipped right at the end of class. And then I'm going to do a section that I skipped about the normal lines. Rewatch this video or parts of this video as many times as you need to be able to absorb as well as you can what we're talking about. Alright, so next topic. We talked a little bit about higher order derivatives, and I want you to find the second derivative of this equation. And what I would like you to do is I'd like for you to pause the video, work it out on your own, and then start the video again and compare answers with me. I do have faith in you that you can at least get the first several steps down. So pause the video now. And now I'm going to start it again. So let's start by taking the first derivative of our situation. In the first derivative, we get 2x plus 2y dy dx equals 0. And I want to, before I take the derivative, I do recommend that you solve for, or before you take the derivative again, I recommend you solve for the first derivative, like we did in class today. So 2y dy dx equals negative 2x. Divide by 2y, divide by 2y. And we end up with dy dx, or the first derivative, is equal to negative 2x over 2y, or in other words, negative x over y. Now I'm going to take the derivative of my derivative, and I'm going to get out of this my second derivative. And then on this side, this is a quotient rule. You do have to still use the quotient rule. It's going to be a ho d high minus high d ho all over ho ho. Now, you're not done here. First of all, you should simplify. I mean, just, again, you only don't simplify on the basic skills test. After that, you have to simplify everything. But besides that, notice you still have the derivative inside the second derivative. We don't want our answers to look like that. We want to see just an equation that you can plug into your calculator or into Desmos, whatever you're using. So I do have some cleaning up to do. And this is the part that if you didn't get it when you did it on your own, that's okay. Let's do this part together. Let's see, it's going to be plus x dy dx all over y squared. And if I come back up here, my dy dx was equal to that negative x over y. I'm going to substitute that in. So just like with the last problem I did, the rule of the game really is substitution. There's very little calculus I'm doing in this problem. Most of what you're watching me do is centered around doing the algebra. And I've said before, the calculus is actually the easiest part of this class. We're really going to make sure that your algebra skills and your trig skills are superb by the time we're finished with this class. And for me too, I can say for me as a student, I learned more about algebra and trig in my calculus class than I ever felt like I really did in my algebra class. Nothing against the algebra. I learned so much in my algebra classes, but it just was using it in such a different way in my calculus classes that it made a difference, and I learned it to a depth that I hadn't anticipated. All right, so I've got a fraction times a fraction right up here. Again, let the paper do the work for you. We're going to square that. We got y on the bottom, y squared here. I think probably the best thing to do next is I'm going to give it a common denominator on the top. You might have a slightly different way of going about it, but we'll get the same answer in the end. While I'm at it, let's go ahead and give that y some legs. I get negative y squared over y, and then a minus x squared, and all of that over y squared. Remember, the reason for common denominators is I can't add them together otherwise and put them in the same fraction. And now you got to think about my little sister. Y squared minus x squared over y. Take the second function, flip them upside down, and we get out of that negative y squared minus x squared all over y to the third. One more substitution. Remember how up here, if I scroll, the equation I was using, I know that x squared plus y squared is equal to 25. I actually can use that to my advantage because I have an x and y squared right here. This won't always work out, but it happens to work out here. If I factor that negative out and just switch the order, I can substitute in the 25. So, in other words, and again, I know that we spend so much time, sometimes these problems are so long we forget what we were doing in the first place. If I have my equation is x squared plus y squared equals 25, then I know that the first derivative of that equation is going to be negative x over y, And the second derivative of that equation is going to be negative 25 over y cubed. Now, I know you're probably questioning, why do we even need to do a second derivative? Because after all, the first derivative is the slope of the tangent line. I will not leave you in the dark for long, but basically all of chapter 3 is really going to be using our first and second derivatives especially. Not so much, like I said in class, not so much your third, fourth, fifth, but first and second derivatives are going to be huge for what we're going to study in chapter 3. So I just want you to start practicing, because we're going to be in chapter 3, not next week, but the week after. Okay, so when you're doing higher order derivatives with implicit differentiation, ultimately what I want you to get out of that problem is that idea of substituting in whatever you need to substitute in to simplify it as much as you need to simplify it. Look at the back of the book, compare your answers, ask me for help. I'll go through and work it out step by step for you and with you. But give it a try. Now, there was one more topic that we didn't get to. I mentioned in class, enough perhaps to get you started, but I don't think enough that you're going to feel comfortable with it. So the last thing I want to talk about was the idea of normal and orthogonal. Now, in your math classes up until this point, you have heard the words right angle, 90 degrees, and perpendicular. As I said in class, we have 2 more words for the list. There are very, very slight reasons why we use these different words instead of just saying everything's perpendicular. They're so slight that I don't think that they'd make really a difference to you. So just know that we're going to use them fairly interchangeably. And as I said in class, these right here are going to be the words you use in K through 12. These words right here are going to be the words you use in college. You're really not going to see much of the word, even perpendicular, you're not going to see a whole lot of in college. But just know that that's what that means. You're going to see normal a little bit more in physics because of the normal force. And you're going to see orthogonal more in your math classes. So let's talk first about the normal lines. So if you have a curve, and I'll do this, I'll make sure the problems that I do for you, I'm going to put them on Desmos too so you can see. We know that if we pick some point on the curve, it has a tangent line that we've talked plenty about tangent lines. It's a line that only goes through that one point on the curve, no other points, within close proximity at least. What a normal line is it's going to be the line that's perpendicular to the tangent line. It's not going to be so crazy awful to solve for, even though it might look a little bit complicated. It's going to add one extra step, is really all it's going to add to our problem. So, like I said in class, the slope of 2 lines that are perpendicular are called opposite reciprocals. So 1 and 2. Opposite reciprocals. Opposite because it's got the negative sign there. Opposite just means opposite sign. Reciprocal means you gotta think of my little sister. You take the thing and you flip it upside down. So in other words, what we have here is the slope of our normal line will be the opposite reciprocal of our tangent line. So if I can find the tangent line, I can find the normal line. So let's do an example. let's find the normal line of the equation x squared plus y squared equals 25. So a circle with a radius of 5, like we talked about today. X squared plus y squared is a circle equation. Whatever it equals is the radius squared. And let's find that at the point 4, 3. I'm going to use my derivative because I do want to find the slope of the tangent line first. There's no way to just jump to the slope of a normal line. So we take the derivative to be able to find the slope of the tangent line of our entire equation. And we get 2x plus 2y dy dx equals 0, like we've gotten on many of the problems before, because we keep taking derivatives of circles. From here, I'm going to subtract the 2x, subtract the 2x. I get 2y dy dx equals negative 2x. Divide by 2y, divide by 2y. And we get the derivative with respect to x is equal to negative 2x over 2y, which simplifies to negative x over y. Exact same thing as before. Now, to find the slope of the tangent line, I know that that slope is the same thing as the derivative, and we'll make sure of the tangent line. I'm going to plug in, again, the point was 4, 3, so I'm going to plug in 4 for the x, 3 for the y, and there's my slope of the tangent line. Now, once you have that, again, super fast and easy, this means by definition, the slope of my normal is going to be, you're going to flip it upside down, and you're going to take the opposite sign, the opposite reciprocal. Now, I want to know the whole equation of the normal line, not just the slope of it, so I do have one step to go further. And again, I think the point slope is the easiest form to use. Form of a line. In other words, a linear line, a straight line. And that again is y minus y1 equals m, x minus x1. What I love about this is I know that my point was the point 4, 3, and I know that the slope that I'm going to use is going to be 3/4. If I take those and plug those in, I'm done. There's nothing else to do. So I want to show you what this looks like, show you why it works. We're going to go ahead, I'm going to open up Desmos, and we'll put the equation, we'll put the tangent line, we'll put the normal line all on there. So my equation was x squared plus y squared equals 25. I'm paying attention to what's happening at the point 4, 3. So I think it's a good idea to put that in just so I have it identified. And you know, one thing I didn't do, I didn't actually find the equation of the tangent line. I didn't ask you to find this, but I'm going to go ahead and put this in. I'm going to find the equation, because again, super quick. Same point, different slope. Still going to be y minus 3, but now it's going to be negative 4/3 here. Everything else is the same. And this is the equation of the tangent line. And if you get confused again about how to put together the point slope form, just remember if you take, let me write it over here. If you solve this for slope, what you have left looks exactly or almost exactly like the slope equation. The only difference is we're not putting 2's on the first y and the first x. Anyhow, we've got y minus 3 equals negative 4/3 times x minus 4. Oops, forgot that was up. So y minus 3 equals negative 4 thirds x minus 4. And we can see very clearly there our tangent line. Let me write up here again, just because we get things we forget. So that is going to be the tangent line equation. If I come down here, let's do the normal line equation. Normal means perpendicular. It's perpendicular to the tangent line. I got the exact same equation, except my slope is the opposite reciprocal. But I want it to go through the same point. So we can see here that we have this right angle that's formed between the tangent line and the normal line. If you are working on these problems with the normal lines, I recommend that you pull it into probably Desmos. Again, you can't graph this function very easily on a TI, but graph it in Desmos and see how you did. See if it's what you expect. Also, convenient thing about this is your normal line goes right through the diameter of your circle. There might be cases where that is the more practical thing to have. Okay, so take a breath. I only have one more thing I'm going to do. One more problem, and that's it. And I want to do something about the orthogonal the orthogonalness, well, that's not a word, of a problem. So, in some of your homework, there are questions that say something like this. Graph the equations and show that they are orthogonal at their points of intersection. And I'm going to do problem 59 in your book. It's not one from your homework, but it looks a lot like them. The equations that they give us there are 2x squared plus y squared equals 6 and y squared equals 4x. So let's start by graphing them. Get an idea of where those points of intersection are. I don't need the points of intersection yet, but I will soon. Soon enough, anyhow. So 2x squared plus y squared is equal to 6, and y squared equals 4x. So I have an ellipse, and I have a sideways parabola happening here. My points of intersection are at the point 1, 2 and 1, -2. Again, I'm going to need those. And my goal is to see where they cross, does it make a right angle? Now, technically, yes, they're both curves, but they're tangent lines, or in this case, really, they're normal lines, or either. Tangent lines, actually, they'd work just fine. You want to show that they're orthogonal or perpendicular to each other. So, we just found the points of intersection are at 1, 2 and 1, -2. I want to compare the slopes of, we'll do the tangent line. I think that would be easier, no point in doing a reciprocal. And I'm going to take the derivatives of each of these separate, and then we'll show if they are orthogonal to each other that way. So the first equation, and set up the second equation, but I'll come back to this one. All right, so the first equation, the derivative would be 4x plus 2y dy dx equals 0. Solve it for dy dx. And I know I'm kind of skipping, well, I'm not really skipping a step here, but I'm simplifying as I go. So there's my derivative of my first thing. On the second thing, take the derivative, I get 2y dy dx equals 4. This one's got just one step to solve, 4 dy dx. Let's see, we can simplify that, so that'd be 2 over y. Now, there's a reason they asked us to do this at the points of intersection, because obviously these equations are not perpendicular everywhere. It's just at those points we want to check. So what I'm going to do is we're going to compare the slopes that we get out of this. So I'm going to call this one slope 1, and I'm going to do this for the point 1, 2. If I plug in my 1, 2, if I plug in my x and my y, I get 2 times 1 over 2, which is negative 2 over 2, which is the same thing as negative 1. And for the same point here, I'm going to call this slope 2 because it's my second equation. I have 2 over y. I plug in my y value. I get 1. And negative 1 and 1 are, in fact, opposite reciprocals. And I know there's no fraction involved here, but I could think of this as negative 1 over 1 and 1 over 1. And if I rewrite them that way, I can see that if I flip 1 over 1 upside down, I still get 1 over 1. So it's just mostly the negatives that we have to account for here. Now that's only going to be true if your slope is 1. If you get any other number, then you want to watch for that reciprocal on the fraction. All right, so that means that the equations are orthogonal at the point 1, 2. And I need to check one more time because it also wanted me to check for the other point of intersection. So I'm going to do the process again. Let's see, this was 1, and then the y here now is negative 2, which is going to be negative 2 over negative 2, which equals 1. On this side, when I plug in to my slope equation, the 2 over y, I get negative 1, and again, 1 and negative 1 are opposite reciprocals, which means the equations are orthogonal at the point 1, negative 2 as well. Now, if you feel overwhelmed by this, 100% yes, like that's going to happen. I'm going to stretch your brain. My goal is that by the end of the year, as we keep going through, you're going to have learned so much. And again, not necessarily always the master of it, but I really think you're going to do pretty well as we keep going. Just keep pushing yourself. That's really the biggest thing. And again, a lot of the students who are doing the best in the class are the ones who visit me at office hours, who are just straight up honest and say, I don't get this problem. Can you help me? And usually I just have to help with a small piece. And they go, oh, okay, yeah, I got that. So if you're not visiting me during office hours, please come by. These problems, the best thing to help you solve them is just experience. The more experience you get for yourself, the better. I've got some experience that I can draw on to help you with the problems. There really isn't any golden egg of this variety. There's no magic spell that makes you know math. It's just experience. And I know, especially with last year and the situations that happened, don't necessarily have as much experience. But honestly, too, even if you had, these questions would be challenging for you. They're meant to push you. They're meant to really increase your capacity. So just keep pushing yourself. Come to my office hours. If you'd like to schedule time outside of my office hours, either because it doesn't work or whatever reason, just let me know. Those times, those of you that still have to take the basic skills or to pass that, I could meet for office hours during those too. For the rest of you who have passed the basic skills and I've not been emailing and harassing, just in the afternoons after lunch, I'm free. Well, I mean semi-free. I kind of do have things scheduled, but I can schedule time to work with you as well. Just as long as you email me and ask me. Okay. With that, I want you to give the homework a try. I want you to do the very best you can. I want you to finish it. So in other words, if you're struggling, come see me. Let's work it out together. Do not wait until Friday, especially Friday after 11, because then you are more on your own. But come see me and we'll work it out.